will continue with the one dimensional numerical integration that we are discussing in the last class, and we have seen in the last class that if for a 3 node element, if the nodes are uniformly distributed, that is if node 1 is at x is equal to 0, node 2 is at x is equal to half, node 2 is at x is equal to L over 2, or if the length of the element is 1 half, and node 3 is at L, or if the length of element is unity, then node 3 is at x is equal to 1. If the nodes are uniformly distributed, then Jacobian is constant. In that case, there is no problem in evaluating the integrals, like what we have seen in the for general one dimensional boundary value problem like kk, kp, k alpha, such kind of integrals, and rq, r beta, such kind of integrals. We can, since the integrand is going to be much simpler, we can actually evaluate these integrals using closed form, in a closed form manner, using the integration techniques that we have. But when the integrand is complicated, then we need to adopt numerical integration, and also adopting numerical integration is easier if we are trying to automate this finite element code. So that is the reason why we are looking at this numerical integration. In finite element literature, the Gauss quadrature is usually preferred because it requires fewer function evaluations as compared to other methods for comparable accuracy. This is what we have discussed in the last class, and also here basically what I am doing is briefly I am reviewing what we have done in the last class before I proceed further. So in Gauss quadrature, integrand is evaluated at predefined points called Gauss points, and the location of these Gauss points are derived in such a way that with n points, a polynomial of degree 2n minus 1 is integrated exactly, and more details you can find in any of the standard books on numerical analysis. So once we evaluate integrand at some predefined points, multiply the integrand value at those points with some weight. So the sum of these integrand values multiplied by appropriate weight called Gauss weight gives an approximation to the integral. So this is how we try to evaluate integrals using Gauss quadrature. For example, a function which needs to be integrated from -1 to 1 can be approximated as function evaluated at some predefined points, n number of small n number of points, x here I takes values 1 to n. So at predefined points x1 to xn, evaluate the function and multiply with corresponding weights of those points like w1 to wn, and so xi is Gauss point, n is total number of Gauss points, w is Gauss weights, function or the value of integrand at the Gauss point xi is fxi. Also in the last class we have seen points and weights, Gauss points and weights up to 10 number of points, and the tables are reproduced here. In the last class, the values corresponding to n is equal to 1 are not shown, but here it is included. So, how to read this table? Here this table is partial, it shows from n is equal to 1 to n is equal to 5 what are the Gauss points and corresponding weights, and how to read this table. Please note that Gauss points you have plus or minus xi. So, corresponding to n is equal to 1 only one point, that is 0, there is no plus or minus 0. So, 1 point, and the corresponding weight is 2. When you decide to go for 2 points, Gauss points, and that is if you want to integrate a polynomial of degree 2n minus 1 exactly, then you need to select n number of Gauss points. So, if you select n is equal to 2, you can integrate a polynomial of degree 3 exactly. So, in similar manner we can select how many Gauss points we can use for some for a particular integral depending on the order of polynomial of integrand. So, when n is equal to 2 is selected, you can see here from the table Gauss point coordinate is given as 0.57735 and a space is there, after that 0 2691, again space 89626. So, here depending on the number of significant digits that you require for the accuracy, you can select either all the significant digits or you can chop it off after certain number of significant digits. So, that is the reason why a space is there in the table. So, for n is equal to 2, the Gauss points are minus 0.57735 if I decide to take 5 significant digits, and the other Gauss point is 0.57735, and the weight of these 2 points is equal to 1. So, that is how you can read this table. And now when n is equal to 3, there are 3 Gauss points. First Gauss point is minus 0.77459 and the weight is 0.55555, and the next Gauss point is 0, weight is 0.888, and the third Gauss point is 0.77459 and the corresponding weight is 0.555. So, that is how you can read this table to get integration points and weights, and once you know the integration point, evaluate the integrand at the corresponding point and multiply with the corresponding weight and sum up over all the points, then we get the approximate value of the integral. And here n is equal to 1 to n is equal to 5, the integration points, coordinates and weights are shown, and in the next table n is equal to 6 to n is equal to 8 are shown, corresponding points in weights. The way you have to read this table is similar to what I already explained to you. and n is equal to 9, n is equal to 10, number of Gauss points n is equal to 9, n is equal to 10 are shown here, the details of points and weights. And if you require more number of for more number of points and the corresponding weights and coordinates, you can refer any of the commercial softwares like MATLAB or Mathematica, and some of these software directly give for any number of points the corresponding coordinates and weights. So now let us try to evaluate an integral numerically using Gauss quadrature. Let us take an example. Evaluate the following integral using Gauss quadrature. Integral 8 x power 7 plus 7 x power 6 integrated from -1 to 1, and here integrand is 8 x power 7 plus 7 x power 6. We can also integrate this in a closed form manner, because integral x power 7 is integral x power 7 dx is x power 8 divided by 8. Similarly, integral x power 6 dx is x power 7 divided by 7. So, we can plug in the limits of integration and evaluate exactly in a closed form manner the value of this integral. It can easily be verified that the exact value of integral is equal to 2, but that is not the purpose of this lecture. We are trying to evaluate this integral using, or we are trying to learn to evaluate this integral using Gauss quadrature. And you can see here the integrand order of polynomial is 7. So, you can back calculate how many points of Gauss quadrature, exactly gives or how many Gauss points gives exact solution. Since the order of polynomial is 7, so 2n minus 1 is equal to 7. So, you can back calculate n is equal to 4. So, when we adopt 4 Gauss points, we are going to get this integral value exactly. So, now let us try using 1 point, 2 point, 3 point and also 4 point, and let us see how the solution converges. So, using 1 point formula, that means we decided to use 1 point Gauss point and the corresponding weight. For n is equal to 1, the coordinate is 0, weight is 2. So, only one integration point is there and the corresponding weight is indicated there, and also evaluate the integrand at x is equal to 0, that is f(x1) is equal to 0. If you evaluate, that is substituting x is equal to 0 in integrand, that is 8 times x power 7 plus 7 times x power 6. When we plug in x is equal to 0 in that integrand, it turns out that it is going to be 0, and finally function value at the integration point times weight gives us 0. So, 1 point formula, 1 point Gauss quadrature approximates the given integral to be 0, which is not making any sense. So, now let us go to 2 points. So, when we decide to use 2 points, we need to figure out what are the coordinates and weights. So, the coordinates and weights from the table, it can be easily checked, these are the values. So, now what we need to do is we need to evaluate function at these points, that is minus 0.57735, multiply it with 1 and add it to function value at 0.57735 multiplied by 1. So, first integration point, evaluate the integrand, that is 8 times x power 7 plus 7 times x power 6, plugging in x is equal to minus 0.57735 and the corresponding weight 1 is also indicated there. Similarly, evaluate function at the second integration point, which is 0.57735, the corresponding weight is also indicated. So, integral, approximate value of integral is function evaluated at x1 times w1 plus function evaluated at x2 times w2, and the value is shown there. The approximate value of integral is 0.5185185 for the significant digits that are selected here. If you want more accurate or more accurate result, or the solution to more significant digits accuracy, then we need to select the integration points and weights to more significant digits. So, now let us redo this integral evaluations in 3 points. For 3 points, the coordinates and weights from the table, it can be easily read, these are the values of points and weights. So, we need to evaluate function at 3 points, minus 0.77459, 0, 0.77459 and multiply with corresponding weights, integrand value at the first integration point and corresponding weight integrand value at the second integration point and corresponding weight, the third integration point, integrand value at the third integration point, the corresponding weight. So, we now have all the, at all points we have the integrand value and corresponding weights, then we can approximate integral like this. You can see one integration point, when we use n is equal to 1 we got 0, when we adopted n is equal to 2 we got 0.5185, and when we adopted 3 points we got 1.68. So, let us see, still the solution is not converged. Let us see what we get when we use 4 points. So, for n is equal to 4, the coordinates, the corresponding weights are given here. So, we need to evaluate function at the 4 points and multiply with corresponding weights and sum it up. Value of function and weight at the first integration point, value of function and weight at the second integration point, value of function and weight at the third integration point, and similarly at the fourth integration point. So now what we need to do is W1 times fx1 plus W2 times fx2 plus W3 times fx3 plus W4 times fx4, and we get approximate value using Gauss quadrature, adopting 4 points we get integral value to be 2, and if you check it can easily be verified that this is the exact value of integral, because before we started out using Gauss quadrature to evaluate this integral, we noted down the exact solution for this problem, which is 2. So we can use numerical integration depending on the using the number of Gauss points depending on the order of integrand, keeping in mind n point Gauss quadrature integrates a polynomial of degree 2n minus 1 exactly. So now let us see application of this Gauss quadrature to some general one dimensional boundary value problem. And let us solve this heat conduction through a thin fin that we already looked at earlier, using when we are actually looking at 2 node linear finite element applied to general one dimensional boundary value problem. And if you recall, the governing differential equation for steady state heat conduction and convection is as given there, and the corresponding boundary conditions are this. And to develop the element equations, if you recall, what we did is we compared this equation, differential equation corresponding to steady state heat conduction convection with general one dimensional boundary value problem, and identified the corresponding coefficients. And once we identify the corresponding coefficients, we already have element equations for general one dimensional boundary value problem. We can substitute the corresponding coefficients in those element equations to get element equations for this particular case of steady state heat conduction and convection. So we need to make a comparison between this differential equation or this boundary value problem and general one dimensional boundary value problem. This boundary value problem is similar to general boundary value problem if variables are interpreted as given in the table here, which shows comparison of corresponding variables in general form and the specific case of heat conduction and convection. Once we have this kind of comparison, the following quadratic finite element equations can be written directly from general equations by replacing the corresponding coefficients in general one dimensional boundary value problem with the coefficients corresponding to this specific case. Note that k x p q are assumed to be constant over element, and the element equations for steady state heat conduction convection are these, where k k k p r beta r q are defined. And these coefficients, we have already seen this meaning of these coefficients when we are actually solving the same problem using 2 node linear finite element method. So, k x x is coefficient of thermal conductivity, h is convection coefficient, p is perimeter over which convection is taking place, a is area of cross section, t is T infinity surrounding fluid temperature, d is nodal vector of nodal temperatures, n is vector of shape functions, and this is here we are dealing with 3 node quadratic element 1D element. So, the corresponding shape functions in parent element n1 n2 n3 are shown there, and the derivatives of shape functions, which is denoted with b, bold letter B, is obtained by taking derivatives of shape functions n1 n2 n3 with respect to s and multiplying with ds over dx, which is 1 over j, j is Jacobian for a 3 node element is defined like this. All these things we have already seen repeatedly many times. So, now we have all the quantities, we need to plug in all these into the matrices k k k p r q and evaluate integrals and simplify and get element equations. After solving for nodal temperatures, complete solution over each element can be obtained using shape functions, just interpolation using shape functions once we know the nodal values of temperatures. And for a 3 node quadratic element, we can derive these shape functions n1 n2 n3 using Lagrange interpolation formula. So, this is required for post processing. Once we get the nodal temperatures of all temperatures at all nodes, to get complete solution over element, we need to do this kind of interpolation. And now let us look at example which we already solved using 2 node linear element. Once again we solve this problem using 3 node quadratic element, and while doing so we also learn application of numerical integration. So, the problem statement is here: determine steady state temperature distribution in a thin rectangular fin shown in figure, the fin dimensions and also temperatures of at the inside wall and also ambient air temperature, and also material properties like coefficient of thermal conductivity, convection coefficient, all these are given, and the schematic shows the rectangular fin. And now perimeter per unit length is, there are two, the temperature convection takes place from top and bottom surfaces, or assumed to be taking place from top and bottom surfaces. So perimeter per unit length is obtained using this formula, 2 times 160 times unit length, and from the dimensions given we can easily check area of cross section. Thickness is given as, thickness of rectangular fin is given as 1.25 millimeters, and width is given as 160 millimeters. So we can find area of cross section. Entire domain of this rectangular fin is divided using 2 quadratic elements with 5 nodes equally spaced, and the nodes are the temperature corresponding to each of these 5 nodes are shown: T1, T2, T3, T4, T5. T1 is given from the problem, it is given as 330 degrees centigrade. Here in the figure there is a typo, it should be 330 degrees centigrade, and for element 1 the nodes are 1, 2 and 3, for element 2 nodes are 3, 4, 5. Again there is a typo, it should be element 2, it is printed as element 1. The ambient temperature is given as 30 degrees centigrade. So T1 is equal to 330 degrees centigrade, T5 is equal to 30 degrees centigrade. Subjected to these 2 boundary conditions, we need to solve this problem of steady state temperature distribution over this rectangular fin. So this is the discretization that is adopted for solving this problem, and if you notice that this temperature, the boundary conditions at T1 or at node 1 and node 5, both of these are essential boundary conditions, and 2 nodes, 2 elements are there, and each of the element, all the nodes are spaced in the same manner. So element equations for element 1 and element 2 are going to be identical. So if we derive element equations for element 1, element 2 equations also look similar. So to derive the element equations for element 1, we need to evaluate some of the integrals between -1 to 1, k, k, kp, such kind of integrals. So we will be using numerical integration to evaluate these integrals with 2 Gauss points, adopting 2 Gauss points. The coordinates and weights of each of these Gauss points are indicated there. So for element 1, 3 nodes, the corresponding nodal coordinates x1, x2, x3 are shown, and once we have x1, x2, x3 values, we can easily evaluate what is Jacobian J. We can easily calculate Jacobian value, which turns out to be a constant 30, because all the nodes are equispaced or uniformly distributed. And now to evaluate the integral kk, please note that kxx thermal conductivity is constant, coefficient of thermal conductivity is constant. So, it is taken out of the integral and we need to evaluate integral minus 1 to 1 b transpose j ds, and that can be evaluated using one dimensional numerical integration by selecting two Gauss points. So, integral kk can be approximated as evaluation of integrand at each of these Gauss points, multiply with corresponding weight and sum it up. So, that is what is shown there, and j is constant at both integration points, which is 30. So, substituting all this, and also b, which is a vector of shape function derivatives. So, once we have these quantities, we can plug in and get the integrand value at integration point 1 multiplied by weight simplified form of that, and shape function derivatives at the second integration point, integrand value multiplied by weight at second integration point, and simplification of this gives and also adding the contribution at the 2 points, we get approximate value of kk using 2 integration points. And now the second integral, which is kp, this can also be evaluated using 2 integration points. The details are given here, weight times integrand value at integration point 1 plus weight at second integration point multiplied by integrand value at second integration point. And similar to the earlier integral where we evaluated derivatives of shape functions vector at each of the integration points, we need to evaluate here shape function vector at each of the integration points, shape function vector at first integration point, integrand value multiplied by weight at the first integration point, and carrying out vector multiplication we get this one. Now, shape function vector at second integration point, integrand at the second integration point multiplied by weight at second integration point is equal to this one. So, now we have integrand value at the first integration point times W1, integrand value at second integration point times W2, add these two together, adding the two Gauss point contributions together, we get Kp value. So, this is how we can evaluate integrals using numerical integration. And now one more integral is left, RQ. RQ is defined like this, and using 2-point integration, integrand multiplied by weight at first integration point plus integrand multiplied by weight at second integration point. The details are shown, and substituting the corresponding values of shape functions at first integration point, second integration point, and summing up we get this one. This is RQ. And here we adopted 2 point for evaluating all the integrals. We adopted 2 Gauss points, assuming that when we adopt 2 Gauss points we can integrate a function of order 3 exactly, assuming the function of in the integrand is of order 3. We adopted 2 Gauss points. Usually in finite element method 2 point integration is adopted, but if somebody requires or if they can guess the order of polynomial in the integrand is higher, then we can go for higher order Gauss quadrature, that is using more than 2 number of Gauss points. So now let us look at, these are the matrices matrices and vector corresponding to element 1. What about element 2? Element 2, locally the coordinates of node 1, node 2, node 3 are shown there, and all the distance between each of these nodes and the total length of this element 2 are same as that in element 1, and also Jacobian is same as element 1. So element equations are same as those for element 1. So we do not need to go through the entire numerical integration details for element 2, because all those matrices and vector value are same. So now let us assemble. So we have element equations for element 1, element equations for element 2. So we can assemble element quantities. Only thing is we need to note that at each there are 5 nodes in this problem based on the discretization that we adopted, 2 quadratic elements, total 5 nodes. So global equation system is going to be 5 by 5, and node 1 contribution goes into 1, 2, 3 rows and columns, because node 1 comprises of nodes 1, 2, 3, and node 2 element 1 contribution goes into 1, 2, 3 rows and columns, because element 1 comprises of nodes 1, 2, 3, and element 2 contribution goes into 3, 4, 5 rows and columns, because element 2 comprises of nodes 3, 4, 5. So the matrices in the global equations are 5 by 5. Locations of element matrices in the global equation are given here, the contribution from element 1 where it goes in to the global equation system, and contribution from element 2 where it goes into the global equation system. So local to global relation is given. So now we can, using this we can directly write global matrices K, K, Kp by plugging in the contribution of element 1 and element 2 into the appropriate locations and global RQ. So once we have all these matrices, complete global equations can be obtained, which is going to be 5 by 5 equation system. And now here, before we proceed to solve for nodal temperatures, we need to make substitution of essential boundary conditions that are given. T1 is equal to 330 degrees centigrade, T5 is equal to 30 degrees centigrade. So, substituting essential boundary conditions and deleting or eliminating first and last equation, we get this. Middle three equations give the remaining unknown temperatures. So, we get this equation system. To solve for T2, T3, T4, we need to rearrange this. And rearranging this, we can solve for T2, T3 and T4. Solution is given here, and T1 is given, T5 is given. So, now we have all the temperature at all the nodes. So, now we can go to each element. Complete solution can be written by using shape functions. For element 1, which goes from 0 to 60, the corresponding nodal coordinates and temperatures are given, are shown there. Temperatures we just obtained after solving the global equation system. So, using shape functions n1, n2, n3, using the coordinates of nodes, we can interpolate temperature inside element 1 using this equation, which can be further simplified, and also derivatives. T is a function of x. So, we can take derivative of t with respect to x, that is also given there. So, this is for element 1 using temperatures at node 1, 2, 3, and for element 2, which goes from x is equal to 60 to 120, and the nodal the coordinates of 3 nodes and the corresponding temperature, local temperatures at the nodes. Here temperatures are given in terms of local node numbering. T1 corresponds to T3, T2 corresponds to T4, T3 corresponds to T5 in the global sense. So, once we have this, we can interpolate using n1, n2, n3 calculated based on the nodal coordinates for this element. So, plugging in these values, we can interpolate temperature at any point inside element 2 and also derivative of temperature at any point inside element 2. Once we have these relations, we can plot temperature as function of x and derivative of temperature as function of x. And here if you recall, we solved same problem using 3 linear elements, and here in this figure solution obtained using 2 quadratic elements is compared with solution obtained using 3 linear elements, and you can see solution is fairly close, that is solution obtained using 2 quadratic elements and 3 linear elements are almost close to each other, but there is a great discrepancy in the derivative of temperature solution that we obtain. So, here temperature derivative of temperature is not we are what we are calculating, we are actually calculating t and forcefully taking derivative. So, that is expected a large error in derivative of temperature, and so this demonstrates using usage of higher order elements, and we also have seen while doing this example, we have seen how to use numerical integration for evaluating some of the integrals required for assembling the element equations.